Static equilibrium is a state where an object is at rest and the net force and net torque acting on it are zero. Static equilibrium is important in engineering applications such as bridge design, building construction, and machine stability. The fundamental equations are sum of forces equals zero and sum of moments equals zero. Engineers apply static equilibrium principles to design stable bridges that can support heavy loads without collapsing. Engineers calculate various forces acting on bridge components, including gravity from the structure's weight, tension in cables, compression in beams, and reaction forces from supports. Static equilibrium requires that the sum of all forces and torques equals zero. Consider a simple beam bridge with weight W supported by reaction forces R1 and R2. Equilibrium equations ensure forces balance vertically and moments balance around a point. These calculations help engineers determine safe component strengths. Static equilibrium is critical in building construction to ensure structural integrity and prevent collapses. Buildings must resist forces from gravity, wind, and seismic activity through balanced force distribution. Gravity exerts downward forces on all building components. Static equilibrium requires these forces to be balanced by upward support from foundations and structural elements. Wind creates lateral forces that can push buildings sideways. Stability requires the structure to resist these forces through braced frames and proper weight distribution. Earthquakes create dynamic forces that shake buildings. Static equilibrium principles ensure the structure remains balanced during ground motion through flexible design and proper mass distribution. In a stable building, all forces are distributed and balanced through structural elements like beams, columns, and foundations. This creates equilibrium and prevents structural failure. Static equilibrium principles are crucial in machine design to ensure machines remain stable and do not tip over or fail under operational loads. Engineers use two main principles. The sum of all forces acting on the machine must equal zero, and the sum of all moments must equal zero. This prevents the machine from tipping or experiencing structural failure. Consider a lever system. A load force acts downward while a support force balances it. Engineers calculate moments around the pivot point to ensure equilibrium and prevent tipping. For stability, the support force must equal the load force. The moment equation ensures rotational equilibrium. Load force times distance from pivot equals support force times its distance. In an industrial press, multiple forces act on the machine base. A normal force from the ground balances the downward press force, while friction prevents the machine from sliding. Engineers analyze stability by summing forces vertically and taking moments about the base. This ensures the machine neither tips over nor slides during operation. Truss structures are frameworks made of straight members connected at joints, forming triangular units that provide strength and stability. In civil engineering, trusses are commonly used in bridges, roofs, and towers because they efficiently distribute loads through their interconnected members. Engineers analyze trusses using the method of joints, which examines equilibrium at each joint, or the method of sections, which cuts through the truss to isolate portions for analysis. Consider this simple triangular truss with supports at the ends and an applied load at the top joint. Using the method of joints, start at a joint with two or fewer unknown forces. Apply the equilibrium equations. Sum of horizontal forces equals zero, and sum of vertical forces equals zero. Substitute known forces into the equilibrium equations and solve for the unknown member forces. Positive forces indicate tension, negative indicate compression. Frames are rigid structures designed to support loads without significant deformation. Machines are structures with moving parts that transmit forces and perform work. To analyze frames and machines, break them down into individual components using free body diagrams. Then apply equilibrium equations. The sum of forces in x and y directions equals zero, and the sum of moments equals zero. Consider a simple frame, an L-shaped structure with a vertical support, horizontal beam, and downward load. The frame supports the load through its rigid structure. To analyze the frame, isolate the joint where the beam meets the support. Draw a free body diagram showing the load, support reaction, and internal forces. Then apply equilibrium equations to solve for unknown forces. Consider a simple machine, a lever with a fulcrum, input force, and output load. The machine transmits forces through its moving parts to perform work. To analyze the machine, isolate the fulcrum connection. Draw a free body diagram showing input and output forces. Apply equilibrium equations to find the relationship between forces and determine mechanical advantage. The center of gravity, or CG, is the single point where the entire weight of an object can be considered to act. It is the balance point of the object, and for uniform gravity, it coincides with the center of mass. In static equilibrium, the center of gravity is crucial because for an object to remain stable, the vertical line passing through its CG must fall within its base of support. This ensures no net torque causes tipping. The position of the center of gravity directly affects an object's stability. A lower center of gravity makes an object more stable, as it reduces the likelihood of tipping. A higher CG makes it less stable, and a wider base also increases stability by providing more support area. To stabilize an object, engineers can add weight at the bottom or lower the center of gravity. This shifts the CG downward, making the object less likely to tip over, as seen when adding ballast to ships or weights to vehicle suspensions. Conversely, raising the center of gravity destabilizes an object, making it more prone to tipping. This is why tall structures without proper stabilization can fall over, or why vehicles become unstable when loads are placed high up. In engineering, center of gravity principles are applied to design stable structures. Vehicles are built with low centers of gravity for safety, buildings use stable foundations to keep CG within support, and machines are balanced to prevent tipping during operation. In this summary, we recap the key principles of static equilibrium that form the foundation of structural analysis. The fundamental conditions require that the sum of forces equals zero and the sum of moments equals zero for a system to be in equilibrium. Free body diagrams help us isolate systems and identify all forces acting on them, while understanding center of gravity is crucial for stability analysis. Understanding static equilibrium is crucial for safe and efficient engineering designs. It ensures structures remain stable under various loads, optimizes material usage for efficiency, and helps prevent catastrophic failures. These principles apply to bridge design, building construction, and machine stability, as we explored in previous sections. These foundational concepts in static equilibrium serve as building blocks for more advanced topics in statics and structural analysis. They provide the groundwork for studying dynamics, where objects are in motion, and kinetics, dealing with forces causing motion. They also extend to advanced structural analysis methods and more complex stability theories used in modern engineering practice.